Hey everyone, how goes it, and welcome to Computer Science 311, Operating Systems. Today, we're going to go through some introductory topics about operating systems. Here are some of the topics that we're going to address today. And here's some objectives we're going to address today. Now, as we're getting into this, we need to figure out, what does an operating system mean? What does it do? We have to think about how this applies not just to the computers that we know, but about other things that may have an operating system, like a car or an airplane's guidance system, or like a printer or a washing machine or a toaster or any of these different things. What does an operating system do with that? How does it apply to that kind of technology? Now, one way we can start defining this is we can figure out that an operating system is a program that basically acts as an intermediate between a user, the computer, and its hardware. Understanding this, we can figure out some operating system goals. So, even though we haven't defined what an operating system is yet, we more or less know what they need to do. Like, for instance, execute a user's program and making solving problems easier. Make a computer system very convenient to use. And also use the computer hardware in an efficient manner. Now, as we're still kind of exploring this idea of an operating system, let's go ahead and start breaking apart this computer system structure. You can effectively break apart a computer system into four major components: the hardware, the operating system, application programs, and the users. In order to group all of this together, you can view these four different categories as more or less something like this, where a user can use these application programs that interface with the operating system that also interfaces with the computer hardware. But also the computer hardware interfaces with the operating system interfaces with application programs, and that interfaces with the user. Now that we more or less understand what a computer system is, we now need to address the operating system aspect again. So as we're trying to define this, we now realize that this kind of depends on the point of view. As a user, you want ease of use and good performance, and in a lot of cases, you don't care about resource utilization that happens in the background. However, with a shared computer system like a mainframe or a mini-computer, you got to keep all your users happy. This requires an operating system that is a resource allocator and a control program to make efficient use of the hardware. Now, another aspect is users of a dedicated system like a workstation need to have dedicated resources, but frequently share those resources from those servers. Now, other perspectives like mobile devices like a smartphone or tablets are pretty poor when it comes to their resources, but they're optimized for the usability and their battery life. Some computers don't really have an interface whatsoever, like embedded systems. So as we are still trying to define what is an operating system, the thing is, the term operating system, it does cover a lot of different roles. There is a lot of different design and uses for operating system. You can find operating systems in a lot of different devices, not just a general purpose computer, but like toasters or spacecrafts, game devices, TVs, and other things. All of this started to come into frame when computers started to become more general purpose. They were no longer needed to solve one problem. We wanted it to solve a lot of different problems. So now we get to the definition of an operating system. There isn't one. Now, even though we can't come up with a good definition for an operating system, the thing is, whenever we have this one program that runs all the time, that does have a definition. That thing is called the kernel. It is the persistent program that is running, and in a lot of cases, people view the kernel as the operating system. Now, aside from the kernel, you have other things as well that interfaces with that, like a system program and also application programs. In a lot of cases, today's modern operating system also includes something called middleware, and that's just a set of software frameworks that provide additional services to application and developers, such as databases, multimedia stuff, graphics. Now let's take a look at an overview of some of the computer system structure. As we're better understanding these operating systems, we do need to look at the computer systems organization. One thing to keep in mind, all of these different hardware devices share what's called a system bus. This is how we can connect all of these various devices together, whether it be the central processing unit, various I/O devices and their controllers, and also the main memory, all move around the information using a bus. Now, input and output devices and the CPU run concurrently. So the way that you can think about that is each one of the I/O devices has a controller that's in charge of that device. Now, each one of these also has a local buffer. And remember, a buffer is just a small piece of memory that we can store information that we can flush out. Along with that, the devices themselves have an operating system device driver in order to manage that input and output device. The central processing unit moves that information from into the main memory and from into those buffers. Input and output is from the device to the local buffer's controller. Now, the device controller informs the CPU that it's finished by that operation using a mechanism called an interrupt. Interrupts are essential to operating systems, and what this does is transfer the control to the interrupt service routine, and generally we keep track of that using a data structure called an interrupt vector. Now, going into a little more depth, an interrupt architecture has to save the addresses of the interrupt instructions. Interrupts can also be software generated by either a trap or an exceptional case. Now, these can be caused by an error or user requests. Now, one way that you can kind of view this is we have these different devices right here. Like, for instance, we've got our CPU, and as we can see, up here it's running some sort of user program, and down here it's being interrupted by some sort of input and output device. Now, as we can see here, this input-output device, it's running idly right now until it gets that I/O request. Then it starts transferring the information over, and then it indicates to the CPU that the transfer has completed. Which now, the I/O device, as this transfer has been completed, it goes back to idle, but inside of the user program, we have to interrupt that in order to transfer that information over. Now, once the interrupt's been handled, we resume back to the user program until another request happens, and then, when this interrupt is signaled, we go back to here, basically pausing this user application, and then once it's been handled, we resume back. Interrupts are absolutely essential to how an operating system is controlling these different devices. Now, in order to handle these interrupts, the operating system has to preserve the state of the CPU, and this requires storing registers and program counters. Now, this also determines what kind of interrupt has occurred, and generally, you separate the segments of code to determine what action should be taken for each one of those interrupts. Now, as we can see over here, we have our devices, the CPU, and this I/O controller, which is controlling an I/O device. Now, if we start from right here in the CPU, some device has now initiated some sort of I/O interrupt. We then initiate the input and output sequence. Transitioning from here, if the input is ready or the output's complete, or the error generates some sort of interrupt signal, that's when we send it over to the CPU saying that we have received this interrupt and we need to transfer the control to the interrupt handler. Once that happens, the interrupt handler processes this information and then returns from the interrupt. And finally, once it's returned from here, once again, the CPU resumes the process that was interrupted by that task and then goes back up to here. Now, as this device driver is being initiated with this I/O, in between this step and these steps here, the CPU is constantly checking for those interrupts between each one of the instructions. Now, in order to handle these I/O structures, there's really two methodologies. The first one is after the I/O starts. Basically, you return control only when the I/O has completed. The other way to look at it is you return control without waiting for the I/O completion. Looking into this a little further, if we take the stance that we return control to the program only after the I/O has completed, first we gotta send a wait instruction that idles the CPU to the next interrupt. Then we continue to loop and wait. After that, at most one I/O request is outstanding at a time and no simultaneous I/O processes can happen. Now, in the other stance, what we can do there is not wait for the I/O to complete. One subcategory of this would be a system call, and this requests to the operating system to allow the user to wait for some sort of I/O completion. A data structure called a device table contains the entry for every one of the I/O devices indicating the type, the address, and its state. Operating system also indexes into the I/O device table to determine the device of the status and to modify entries in the table to include those interrupts. Now let's go into the storage structure of a computer. We can really divide this into two sections: main memory and your secondary storage. Your main memory, which I'll basically refer to as memory, is your random access memory. It is your RAM. Typically, your main memory is volatile, which means as soon as you turn off the system, everything that was in that memory is gone. It's wiped out. Now, typically, when we refer to random access memory, this is in the form of dynamic random access memory, or DRAM. Your secondary storage is more or less an extension of your main memory that provides a lot of storage that is non-volatile. So when you turn off your system, you don't lose that information. Now, some of the common secondary storage is a hard disk drive, an HDD. Now, this is usually some sort of platter-based system that's made out of metal or some sort of glass, but either way, you have some sort of magnetic surface to record this information. This surface is then logically divided into what we call tracks, which are then further subdivided into what we call sectors. The disk controller is a device that determines the logical interaction between the device and your computer. You can also have non-volatile memory, NVM, which are faster than hard disks, and they're still non-volatile. These are starting to become more popular as capacity and performances increase and also as the price drops. So now that we understand the different types of memory, we kind of have to understand some of the basic elements of the computer. First of all, a bit. A bit is the foundational element of this, and it can only contain two values, 0 or 1, false or true, off or on. When we start grouping those into a larger structure, 8 bits compose a byte. And this is usually most computers' smallest and most convenient chunk of storage. It is what we use to store the information in your main memory and your secondary storage. Everything in a computer is just a number. Now, going a little further from that, another term is called a word, which is the computer's given architecture's native unit of data. A word is made up of one or more bytes. So, for example, a computer with a 64-bit register and a 64-bit memory addressing scheme typically has a 64-bit or 8-byte word. Now, going a little further, we need to start grouping together these bytes into other structures. Like, for instance, a kilobyte is 1,000 bytes. A megabyte is 1,000 kilobytes. A gigabyte is 1,000 megabytes. A terabyte is 1,000 gigabytes. And a petabyte is 1,000 terabytes. All of these values increase by base 2, simply because everything in a computer is a 0 or a 1. Looking at storage a little further, there's different classifications of storage, and this really depends on the speed, the cost, and its volatility. Caching is a verb that we use commonly for basically copying information into a faster storage system. Main memory can be viewed as the cache for your secondary storage, because your main memory is faster than your hard drive. Now, along with that, you have device drivers that correspond to storage, and each one of those controls to manage the input and output of this storage. This basically provides a uniform interface between the control and the kernel. Now, looking at this is a way that we can start dividing up the storage hierarchy inside of a system. As we can see right here, your registers are your fastest storage devices. Then below that, you have your cache, followed by your main memory, and this is corresponding to your volatile storage. Now, when we go into non-volatile storage, we start getting slower and slower. So you then have your non-volatile memory, which is a little faster, followed by your hard disk drives, followed by optical disks, so these are called tertiary storage, and then magnetic tapes. A way that we can start looking at how a modern computer works is based on this von Neumann architecture, where we have this central processing unit where we have these threads of execution. Now for every one of the CPUs, we have this level of cache. Now from the CPU to your main memory, you can transfer instructions and executions of this cycle. You can also move the information that's used by this process in this way as well. Now down here, we also have this I/O device that interfaces with the CPU by issuing those I/O requests. We also have the transfer of data and also the interrupt requests that go from and to this device. Now this I/O device might also have direct memory access that can quickly transfer this information from the device to here. Now, for direct memory access, this is used for high-speed I/O devices that's able to transmit the information at a very close memory speed. Device controllers is what transfers the blocks of information from the buffer storage directly to your main memory without having to use the CPU. Now, only one interrupt is generated per these blocks, rather than one interrupt per byte. Now, going further with this, an operating system has a series of operations. First thing is you have your bootstrap program, and this is a very simple piece of code that just initializes your system to then load the kernel. Your kernel then loads, and that once again is your persistent program that's always running. Once your kernel loads, it starts these system daemons, which the service provided outside of the kernel. Now we introduce the idea of multiprogramming or a batch system. Now, a single user cannot always keep the CPU and the I/O devices busy. A multiprogramming system organizes these jobs, the code and their data, so that the CPU always has something to do. A subset of all of these jobs is usually stored in memory, and one of the jobs is selected and it's run by some sort of job scheduling, which we'll talk about in more depth later on in this class. Now, when a job has to wait for like an I/O, for example, the operating system switches to another job to always stay busy. Now, multitasking with timesharing. Now, this is the logical extension of these batch systems. The CPU is switching jobs so frequently that the user can interact with each one of the jobs while it's running, creating an interactive computing system. Ideally, you want this response time to be less than a second. Each one of the users has at least one programming executing in memory to the process. If you have several jobs that are ready to run at the same time, what the CPU does is schedule those processes. Now, if the processes don't fit in the memory, we gotta swap that information in and out. And virtual memory allows the execution of these processes that are not completely in memory. Now, CPU scheduling and virtual memory are two large sections inside this course, so keep some of these concepts in mind because it will come up later. Now, along with these operating system operations, we do segment it off into a dual mode idea. And so the way that you can do this is separate your user mode from your kernel mode. Doing it in this way helps the operating system to protect itself from other system components. Generally, in order to do this, we have what's called a mode bit that's provided by the hardware, and this is able to distinguish when our system is running user code or that kernel information. And easy enough, when the user is using the system, the mode bit is set to user, and when the kernel is executing, then the mode bit is set to kernel. Now you might be wondering, how do we guarantee that the user doesn't explicitly just set the mode to kernel? Well, a system call is the thing that changes the mode to the kernel. When we return back from that, it automatically resets it to the user, so that mechanism is pre-built into it. Also, some instructions are designated as privileged instructions, and they are only executable in the kernel mode. So the way that we can start looking at this is if we're executing some sort of user process, and that user process calls something that's related to the system. This transfers over to the kernel, and our trap bit is set to 0, so kernel mode. We then execute some of the code that's related inside the kernel until it's completed, and then we switch back that bit to 1, and then we return from that system's call. Another mechanism that's built into most operating systems is called a timer, and this can just be used to prevent infinite loop. So think of it this way. A timer is always set to interrupt the computer after some period of time. We keep track of this, and it decrements by using the physical clock. The operating system sets the counter, and this is a privileged instruction. Now, when that counter reaches 0, it automatically generates that interrupt. We set this up before scheduling a process, that way we can regain control or terminate a program that exceeds some allotted time. Now, one thing an operating system should do is manage your processes. And a process is a program that's currently being executed. It's currently running. The way that you can also distinguish this is the program is the passive entity, while a process is the active version of the program. So keep those separated. Now, in order for a process to run, we need resources to accomplish the task. We need the CPU to run the instructions. We need the memory to store our information. We have to interface with input and output devices commonly with this, and also we need to access files commonly when we're running processes. It also needs to initialize all of the data in the process as well. Whenever a process has completed, in other words, when it has terminated, it requires reclaiming any of the reusable resources, and the operating system has to manage that. Now, assuming we have a single-threaded process, it only has one program counter. Now, the program counter specifies where the next instruction is. Now, processes are assumed to execute instructions sequentially, one at a time, until they have completed. Now, if we had a multi-threaded process, you have one program counter per each one of the threads. Now, typically a system has a lot of processes, some users, and some operating systems running concurrently on one or more CPUs. As we're managing these processes, there's some activities that we need to discuss. Now, the operating system is responsible for the following activities in relation with process management. So, creating and deleting both user and system processes, suspending and resuming those processes, providing mechanisms for process synchronization, that becomes very important, providing mechanisms for process communication, also very important, and providing mechanisms for deadlock handling, also very important. And we go into detail about each one of these later on in this class. Now, moving on from the processor, we have to worry about our memory and how we manage that. So first of all, in order to execute a program, all of it, or part of it, needs to be in your main memory. Now, all, or part, of the data that is needed by the program also must be in memory. Memory management determines what is in memory and when, and we need to optimize the CPU utilization and the computer response to the users by doing this. Now, some of the memory managing activities is keeping tracks of which parts of memory are currently being used by whom, deciding which process, and the parts thereof, and the data to move in and out of memory, and also allocating and deallocating memory space as needed. Exploring more into memory, we have to have a file system that is managed as well. Now, the operating system should provide a uniform logical view of this information. This abstracts the physical properties into logical units, which we call files. Each one of these mediums is controlled by a device, like a disk drive, a tape drive, however. Now, going further with these files, a file system management is usually organized into something called a directory. Access and controls on most systems determine who can access what. Now, some of the operating system's activities include creating and deleting these file directories, primitives to manipulate the files in the directories, mapping files onto the secondary storage, and also to back up the files onto stable, non-volatile storage media. Not just with file systems, we have to concern ourselves with managing mass storage. And now this is usually disks that are used to store data that doesn't fit into your main memory, and it has to be kept for a long period of time. Now, the entire speed of a computer hinges on your disk subsystem and its algorithms. So some of the activities in relation to mass storage would be mounting and unmounting these storage devices, free space management in your system, storage allocation, disk scheduling, partitioning, and also protecting. Now remember, caching was an idea where we copied from slower storage to fast storage temporarily, and this is so very important when it comes to operating systems. Fast storage such as cache should check first to determine if the information is there. If it is, the information is then used directly from the cache, fast. But if it's not, we have to copy that information to the cache and then use it there. Now looking at this, we can see the different types of memory, their typical sizes, and how fast they are. So as you can see right here, your registers are absolutely the fastest when it comes to access time. Then your cache is at the next level, then your main memory, you can see this is getting slower, then a solid state disk, which is very slow compared to this, and then a magnetic disk, which is very slow compared to everything else. Now when we're loading all of this into memory, we have to travel from the slow magnetic disk to our main memory to our cache to the hardware registers. One important element of this is we need to provide cache coherency, such that wherever we're at in this memory, we need to have the correct value. The thing is, you can have several copies of data here, 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 and here, and we have to make sure that all of those remain consistent, or else we will encounter some pretty severe problems. Now another element is your input-output subsystems. And the purpose of an operating system is to hide all the weirdness of the hardware devices from the user. An I/O subsystem is really responsible for memory managing of the I/O, including its buffers, caching, spooling. Now taking a step back for a second, let's talk about protection versus security, because these are two very important principles to operating systems. Protection is any mechanism that controls access of a process or the user's resources defined by the operating system. Protection protects the operating system. Security is the defense of the system against an internal and external attacks. So worms, viruses, identity theft, all of that is related to security. Now, virtualization is increasingly becoming more important. Now, there is a distinction, because emulation is when you emulate the hardware, or when you emulate a CPU type that is different from the target type. Now, when we do this, we use this strategy called interpretation in order to achieve that. Now, virtualization is you have some sort of operating system natively compiled for the CPU that is running guest operating systems that are also natively compiled. Now, in order to achieve this, we have what's called a virtual machine manager that provides the services for virtualization. Computers can become even more complicated than what we have just described, because we can also have what's called a distributed system. And this is a collection of separate, but also possibly, but not necessarily, heterogeneous systems all networked together. We use what's called a network to communicate with these different systems using a protocol called TCP/IP. And this can be implemented using a local area network, a LAN, wide area network, a WAN, metropolitan area network, a MAN, or a personal area network, a PAN. Now, a network's operating system provides features between the systems and across the network. It establishes a communication scheme that allows the system to exchange these messages, and it gives the illusion that all of this is one system. Now we need to look at a computer system's architecture. Now, most systems use a single general-purpose processor. Multiprocessors are growing in use and importance, and these are known as parallel systems or tightly coupled systems. Using multiprocessors give you increased throughput, better economy of scale, and also increased reliability. Now, in multiprocessors, you have two types. You have asymmetric multiprocessing, where each processor is assigned a specific task, or symmetric multiprocessing, where each processor performs all the tasks. A way that you can look at this is, here are two different processors, which have our CPUs that contain the registers and the cache for each one of these, and they all share the bus to the main memory. Now going further with this is called a multi-core design, which in this case, instead of having two processors, you have one large processor that is then subdivided into these cores. And these cores have the registers and the caches, which also share a secondary level of cache, and now these interface the main memory through the bus. Now going further with this, we can start viewing these as a clustered system, and this works like a multiprocessor system, but with multiple systems working together. You can share storage via a system called a Storage Area Network, or a SAN. Cluster systems provide a high availability of services which survive these failures. And just like before, we have asymmetric clustering, which has one machine in what's called hot standby mode, and symmetric clustering, which has multiple nodes running applications monitoring each other. Some of these clusters are for what's called high performance computing, HPC. When we use this, we have to make sure that our applications are written for parallelization. Now, you might have issues with various conflicting operations, and this is where a distributed lock manager comes into play. Let's talk about some computer system environments. A traditional view of a computer system environment is a standalone general-purpose machine. Now, this gets a little more complicated because most systems interconnect with other systems via the internet. Portals allow us to provide web access to these internal systems, and network computers, like thin clients, are just web terminals. Mobile computers are interconnected via wireless networks, and also networking is becoming ubiquitous. Even these home systems use firewalls to protect home computers from internet attacks. We need to protect our smart toasters. Now we also have mobile devices, where they are handheld like smartphones and tablets, etc., and the function is different from the traditional laptop. A lot of cases we've got extra features like GPS and gyroscope abilities, and now we're allowing new types of applications that use what's called augmented reality. We can also view client and server systems. So a computer server system provides an interface to the client's requests, in other words like a database, and a file server system provides interfaces for clients to store and retrieve files. Another type of distributed model is called peer-to-peer, and peer-to-peer doesn't distinguish clients and the servers, they're acting as the same thing. Now instead, all of the nodes are considered to be peers. They may each act as a client, server, or both. Another system is called cloud computing. This delivers computing, storage, and even apps as a service. Now the logic extension of virtualization is this because it uses virtualization as a base for this functionality. There's a lot of types of clouds, like a public cloud that's just available via the internet to anyone, well, who's willing to pay. A private cloud is run by a company for their own company's use, and a hybrid cloud uses both public and private cloud components. Now, also with cloud computing, we introduce these new concepts like software as a service, where one or more applications is available through the internet. Platforms as a service, where software stack ready for applications use the internet. And also infrastructure as a service, where it serves or stores available information over the internet. Here's a view of how we can look at most cloud computing structures. Another type is called a real-time embedded system. Now, real-time embedded systems are one of the most prevalent forms of computers. They're considered very special purpose and have limited operating systems. And in fact, a lot of times they're considered real-time operating systems. Now, going further with real-time operating systems, you have to have a well-defined fixed time constraint. So in other words, processing must be done within some sort of time constraint. And also, correct operation only if the constraints are met. Now, we're going to go into a lot further detail when it comes to a lot of these systems. This has only been an introduction, but before we get to that, it is known that operating systems use very specialized data structures that we need to be aware of. Some of the most common ones that we see are, for instance, a singly linked list, which looks like this, where you have your data that then has a pointer that points to the next node, which points to the next and next. You have a doubly linked list that contains the data and a forward and a backwards pointer for each one of the nodes. You also have a circular linked list where the last element in the circular linked list points back to the first. You also have these things called binary trees, and the rule of a binary tree is left is less than and right is greater than. Now, according to the book, it says that it is less than or equal to, but in most cases, binary trees should not have duplicates. But because they're saying left is less than or equal to right, the search performance is guaranteed to be big O of n, but if we ensure this is a balanced binary search tree, it's log base 2 of n. Another common data structure is called a hash table. What this does is, given a key, you run it through this thing called a hash function in order to find the value. And so that's the end of chapter 1. This has been an overview of a lot of different topics that are related to an operating system. One of the biggest takeaways is understanding that an operating system doesn't really have a clear definition. In a lot of cases, people consider the persistent program, the kernel, as being the operating system. We're going to explore all of these topics much later on. With that being said, I'll see you next time.